Alright, so in this video we're going to prove Menger's theorem, which we recall states that given two fixed vertices in our graph, the minimum size of a vertex separating set between x and y is the maximum number of internally disjoint xy paths. A key part of our proof is going to involve using something called the contraction of a graph, which is sometimes used when studying graph coloring as well. Given a graph G and an edge, uv, the contracted graph, G mod E, has the following vertices. It's every vertex of G except U and V, and then we add in a new vertex, which we call the contracted vertex. And then we say x and y are adjacent if x and y were adjacent in the original graph, and these x and y are not the vertices we deleted, or if y is the contracted graph and x was adjacent to u or v in the original graph. So sometimes a picture helps. Suppose this is our graph G, and this is the edge we're going to contract. Then what we do is we remove these two endpoints, and we kept all the edges that didn't involve those endpoints. And then we've added a new edge called the contracted edge, new vertex called the contracted vertex. And then for every edge that had one endpoint on E, we now put an edge between the other endpoint in our contracted graph. So the reason why we call it contraction is the idea is that we've taken this edge and we've made it shrink down further and further until it became one vertex. And to give an intuition of where we are headed, it's worth noting that this contracted vertex is now a cut vertex here. Now if we decontract it and replace that contracted vertex with its original endpoints of E, you end up seeing that you have a separating set in the original graph. In particular, it turns out that the connectivity of the contracted graph is at most the connectivity of the original graph as a result, because every separating set in the contracted graph can be turned into a separating set of the larger graph that's of size 1 bigger, or at most 1 larger. And so in particular, you can't end up with a situation where the contracted graph has a larger minimal separating set than the original graph. So now we are on to proving Menger's theorem. We're actually going to prove a strengthening of Menger's theorem. Instead of vertices x and y, we're going to work with entire vertex sets A and B. So given two sets A and B, we're going to prove that the maximum number of internally disjoint AB paths is the minimum number of vertices in an AB separating set. Note that neither of these terms have been defined, but they can be defined similarly to how we defined the terms in the case of an XY separating set. Namely, when we're saying internally disjoint AB paths, we're talking about paths that outside of A and B are disjoint. So they can share an endpoint in A or an endpoint in B. It's also clear from the picture that we are requiring the paths to have a start in one set and end in the other. And similarly, we see what a separating set is. It's a set S whose deletion disconnects the graph, leaving A and B in separate components. So this is the result we're going to prove. We're going to prove it by induction on the number of edges. And so one direction doesn't take much effort. Suppose you found a minimal separating set, and suppose we had a collection of disjoint AB paths. Then we see that each path has at least one vertex from the separating set. In other words, we can't possibly have a path in A ending in B that goes around S, because then S is not a separator. And so each path has to meet S in at least one vertex. And because these are disjoint paths, these intersections have to be distinct for different paths. So in particular, for each path, we get at least one vertex in S. And once you pick that vertex for each path and mark it, then we get a separate set of vertices for each path. And so we had 3 paths here, and we have 3 vertices. So this tells us that the number of internally disjoint paths we found was at most the size of the separating set. So this tells us that it's not possible for the maximum number of internally disjoint AB paths to exceed the size of the separating set. Now we need to show that there's equality, namely that if S has size K and is the minimum separating set, then there must be at least K internally disjoint paths. So now we need to describe how to construct these three paths. All right, so we're doing induction on the number of edges, so let's just take an edge in our graph and let's contract it. So this means we have to change our sets A and B. If our edge E had an endpoint in A, then we replace that endpoint with the contracted vertex and we leave B alone, and this gives us our A prime, the second condition, and our B here. Similarly, if the edge had one endpoint in B, then when we contract, we replace that endpoint with the contracted vertex. And we leave A alone. There's this weird case that it's possible that E has an endpoint in both sets, in which case we replace those endpoints with the contracted vertex. And so this gives us an A prime and B prime that actually overlap. If you go back through our definitions, you discover that there's nothing requiring A and B to be disjoint. However, I should make things a bit more clear. In this situation, if A and B are not disjoint, this vertex would be considered an AB path, with the starting and endpoint being the same, but it would also be an element in an AB separator because you'd have to delete it to separate A prime from B prime. All right, now for the next step, we consider the case that there are K internally disjoint paths between A prime and B prime in G prime. Then it turns out this means we have K internally disjoint paths between A and B and G. So given any one of these paths, if it avoids the contracted vertex, then it's actually a path in the original graph as well. So your only concern is if a path goes through the contracted vertex. But then by definition of contraction, this red vertex had to be adjacent to one of those endpoints of that edge in the original graph, and same with the blue vertex here. And so either you can bypass the edge entirely, or you replace that contracted vertex with this edge, and now you get a path in the original graph. Note here I drew the picture so that the contracted edge was did not have an endpoint in A or B, but you could run through the cases. If one of the endpoints was in A or B, then this vertex is in A prime or B prime, and so you're replacing it with an edge that has only one endpoint in A or B. And so the argument still works. So if we have K internally disjoint paths between A prime and B prime, then we have K internally disjoint paths between A and B in our original graph. So then there's one remaining case. Suppose that we don't have K internally disjoint paths between A prime and B prime. Well, since G prime has fewer edges than G, this implies that A prime B prime has a separating set, Y, whose size is less than K, in the graph G prime. Note here that you can go back to the induction hypothesis and remember that the statement to the theorem we're proving by induction is over all pairs A and B. So in particular, we are allowed to apply the induction hypothesis to this pair of sets. And then the last comment we want to make before we go forward is that if the contracted edge was not in the separating set, then you actually have a separating set in the original graph G between A and B. And this is a contradiction because our separating set has size strictly less than K, contradicting our assumption that a minimum separating set has size K. Thus, we must have found a small separating set in the contracted graph. It's just that the contracted vertex is in that separator. Well, now let's just decontract that vertex and add the endpoints of that edge. And now we have a new set called X. So it is worth noting that X is any separator between A and X is also going to be a separator between A and B. That is, if you manage to find a separator S between A and X, that means every path between A and X has to go through S. Well, if you construct any path between A and B, because Y was an A prime B prime separator, every path has to go through Y. That is, anytime you found a path between A and B, if you contract the edge, you're going to get a path between A prime B prime. Since Y prime is the separator, it has to go through, possibly through the contracted edge, which means that in the original picture, this path actually had to go through here, possibly through the edge. And so if S is an AX separator, that means the path also has to go through S. And so the point is, any set that separates A from X also separates A from B. So now let's delete the edge E to create a new graph we're calling G double prime. And since K is the size of the minimum separator between A and B, and S is separating A from B, we see S has at least K vertices in it. And so now we can apply the induction hypothesis to G double prime because it has fewer edges. So by the induction hypothesis, since G double prime has a separator size K, there has to be K internally disjoint paths between A and X in G double prime. So in particular, we're avoiding this edge, but not necessarily its endpoints. By a similar argument, any separating set between X and B has to separate A from B. So then we can apply, so T has size at least K. And so we can apply induction hypothesis on G double prime with respect to X and B to guarantee that there are K internally disjoint paths between X and B. So thus we've created K paths between A and X and K paths between X and B. We note any path, one of these black paths can't go around X to go into B, as noted before. And so the black paths and the red paths cannot intersect outside of X, because if they do, then you'd create another path from A to B. And then X is not a separating set. And so the conclusion is, looking at what you see from the picture, you should be able to glue the paths together to create paths between A and B, exactly K of them. So thus we see the general proof strategy. You contract an edge and then either find disjoint paths in the contracted graph that you can then expand back into the original graph, or you must find a small separator, and then you do this little trick where you find paths between A and the separator, X, and then between X and B.